Okay, I'll join all other speakers, thanking the amazing organizers for organizing this event. I'll start with an amazing piece of art for two reasons. First of all, I wanted to lighten the mood. Second of all, some of you asked me what my title means. So what it means is this. This is an example of what my title means. Okay, this will be about work I did with these amazing people from all over the world. And the motivation for this work comes from two well-known facts. Over the past 15 or so years, it has become increasingly clear that we can be very good at exactly computing path integrals of some supersymmetric quantum field theories on some manifolds. And then also, we have this amazing fact that z is equal to z. So the path integral of certain quantum field theories should be the same as the path integral of a string or n theory on asymptotically locally ADS spaces. And so specifically, we'll be interested here in something beyond the leading supergravity approximation in this kind of identity. So why do we want to do this? Well, the first reason is obvious, I think. We would like to explore how ADS CFT works beyond the leading supergravity approximation, and we've already heard at least two talks about this in this conference. Also, we heard, yes, I'm sorry. We heard that string theory is hard, especially on backgrounds with non-trivial fluxes, and this tool can allow us to kind of learn or access something about it. Finally, the right-hand side of this identity should contain black holes, so we can hope to learn something about black holes. And in this talk, I'm going to focus on 3D CFTs with ADS4 duals, specific duals that are in two-way string theory or 11DM theory. Okay? Good. Let's get going. So first, I'm going to tell you about the QFT part of the story. So this will be about a specific model known as ABJM, which is a specific 3D QFT that has an explicit well-known bulk dual. So here's what the theory is. It's 3D Chern-Simons matter theory. It has UN times UN gauge group and equal and opposite Chern-Simons levels Kn minus K. It also has some matter fields, 4 bifundamental chiros, and some very specific interaction given here in terms of a superpotential. And so when you combine all of these ingredients, the theory for k more than 2 will have n equals to 6 SUSY, and when k is equal to 1 or 2, there's some SUSY enhancement to n equals 8 supersymmetry. So the claim to fame of this model is that it should be the low energy theory of n coincident N2 branes probing C4 mod ZK with some very specific ZK action on the C4. Okay? And I'll be interested in this talk into large n limits of the model. The first one that you can ponder is to keep k fixed and take n large. And in this case, the claim is that the dual is in terms of n theory or 11D supergravity on this space, ADS4 times S7 mod ZK. I want to emphasize that this is a smooth action of the ZK, so it's a completely smooth manifold. And then the length scale of ADS L and the Planck scale can be related to K and N in this way. And another limit, which I'll call the type 2A limit, is when we also scale K with N in some specific way, such that this lambda here is finite. And then the dual is in terms of ADS4 CP3 two-way string theory. Okay? Now that we know what the model is, we can try to compute the path integral. That's obviously hard. But if you put the theory on S3, you can actually do that in terms of supersymmetric localization. There's a very specific matrix model, which I'm not showing here. And after a lot of work, what emerges is an answer that looks like this. So we'll have to unpack this formula. So there's N and K, which I have already introduced. And then these MA and B are certain deformations of the theory on the sphere that are compatible with a certain supercharge. So MA are 3 real masses, and B is a squashing of the sphere. And I should emphasize that this formula for the path integral on S3 in terms of an Airy function, so this AI is an Airy function, has been established for many values of M1, M2, M3, and B, but not for all of these values. So strictly speaking, what I'm showing here is a conjecture which is well motivated and explored in many ways. And also, what I'm not showing here is these exponentially suppressed contributions, which in some cases can also be computed explicitly. Okay, so what is this good for? It teaches us about integrated endpoint functions of the model, as we heard yesterday from Silvio. But it also is just ready to be expanded at large N. And this will be the interest in this talk. So I can just take a log of this formula and expand at large N, and I will find an answer which looks like this. And the leading order term, this n to the 3/2 piece, is well known to agree with the supergravity approximation in 11-dimensional supergravity. And what will be of interest in this talk is these 2 subleading terms, the n to the 1/2 and the log n piece, as well as these instantons here. Instantons. Okay? Good. What you can also do is you can use this kind of Airy function expression and reorganize it as a 2A string theory formula. Again, I'm doing this from the matrix model side, from the QFT side, but the answers can be organized as a 2A string theory answers. And so you get an expected expansion in terms of the genus, and then these FGs here should be thought of as free energies of the worldsheet 2A string theory. And what's amazing is they can be computed exactly. So exactly up to worldsheet instantons, which can be computed only for some special values of the parameters. So what I'm showing here are the values MA equal to 0 and B equal to 1. But this thing here can be done for all values of M and B. And these are nice, simple answers that should be the free energies of these worldsheet strings. And I have no idea how to compute them from the bulk. It will be nice if we can understand this. Okay, so all of this was ABGM on S3. But of course, I can put the theory on other manifolds and try to play the same game, basically. One example that I like is this manifold S1 times a Riemann surface, a smooth, compact Riemann surface of genus G. And then to keep a certain amount of supersymmetry, I will do a certain twist on sigma in terms of the background for the U1R symmetry of the theory. And this path integral has a name. It's called the topologically twisted index, or the TTI. And after a long song and dance, you can evaluate it explicitly, again, by allowing for some kind of arbitrary deformation. So these NAs here are background flavor symmetry magnetic fluxes. These delta 1, 2, 3, 4 are fugacities for electric charges, if you wish. And this specific expression here is an analytic expression, but we don't have an analytic derivation of the formula. So this formula was obtained in some god-awful way in terms of numerics, and I would like to understand how to obtain it analytically, but we think it is true. And the claim to fame of this object is that in the bulk, this should give you the entropy of supersymmetric, magnetically charged ADS Reissner-Norstrom black holes. Okay? And again, although I have not done this on the slides, this can be reorganized as a two-way string theory expansion, and we have done all of this explicitly in our papers. Good. Finally, I want to mention a much more complicated observable, the superconformal index, as it's called. The path integral on S1 times S2 with a certain angular fugacity omega on the S2. In this case, we really don't know how to compute this object analytically to all orders in n, but we can be inspired by Cardy and take a limit where the S1 is much smaller than the S2. This amounts to this omega going to 0 in some specific way. And then in this case, we can evaluate the first two leading order terms, 1 over omega and omega to the 0 terms, to all orders in 1 over n. And again, we find simple analytic expressions like this. And this index, this formula here, captures the entropy of another kind of BPS black holes in the bulk, the Kerr-Newman supersymmetric black holes. Okay, good. So all of this was kind of an overview of the QFT results, and now I move on to the bulk. The first thing I'll be after is this n to the 1/2 term in the large n expansion, and it's kind of clear that this term should be some kind of a leading order higher derivative correction to 11D supergravity. The problem is that we don't know how to compute those. I need all corrections to 11D supergravity at this order, which are not known. So we have two options, either give up or find a trick. We chose to find a trick. And the trick is to go to 4D minimal gauge supergravity and then use the wisdom of the elders in our field, conformal supergravity, to try to constrain the possible leading order higher derivative terms. After some work, we found that there's only two possible terms, this LW2 and LGB, which are some specific combinations of the Riemann tensor and F mu nu, which I'm not bothering you with here. And then the constants, C1 and C2, if I knew how to do it, should be obtained from 11D supergravity of the corrections to it and then reducing that on a sphere or some other manifold. But we don't know how to do that, so at the moment I will keep C1 and C2 as kind of arbitrary parameters. Once we have an action like this, we can do ADS CFT. We can evaluate, for instance, the on-shell action of the theory for any solution of the model, and we did this, and even though the analysis is kind of annoying, the final expression is very, very simple, and it's here on the box. So the on-shell action, the regularized on-shell action in this model is given here, where curly F is the usual on-shell action of Einstein-Maxwell theory, and then chi is the Euler number of this asymptotically locally ADS background. So the upshot here is that if you have a favorite background of Einstein-Maxwell theory, you can evaluate F and chi on it and put it in this formula, and it's going to work. Okay, so now, since I don't know how to obtain C1 and C2 from a top-down construction in M theory, what I choose to do is to think about what are they in the dual CFT, and I know how they should scale. They should go as n to the 1/2, multiply by some order 1 numbers, which I call V1 and V2 here. And then I can translate the answer on the previous slide to this answer here, which now looks like a QFT free energy. Okay? And I can use this and try to compare with known supersymmetric localization results, and I only need two of those. So we choose to use the two-point function of the energy momentum tensor CT, thanks, as well as the free energy on the round sphere. And using only those two data points from the dual CFT, we could fix all these order 1 numbers in red. And then, once we did this, we went back and checked against all these other answers that I showed you. So we're pretty confident that what I'm showing here is true. Good. Now we're going to the logs. So we'll be chasing these log n terms. And to do this, we got inspiration from this work of Ashok Sen from 15 or so years ago, where he emphasized that if you're after the logarithmic corrections to the Bekenstein-Hawking entropy, you don't actually need full details of the UV completion of the theory. You can only use the light modes below the cutoff. And then you should study one loop effects of those light modes in the background of the black hole. So in this case, we sometimes do have a black hole, as in these S1 times sigma examples and S1 times S2, but others we don't have a black hole. So we will be in some asymptotically ADS space, and we'll be studying one loop effects on top of it, and we'll be chasing this log L square over G Newton. L is the scale of ADS. What's important as input from the dual CFT is that all of these coefficients of log n are numbers, simple rational numbers, independent of all of these squashing deformations and mass terms and so on. Even though these leading terms are actually some detailed functions of those, the log term is always a simple rational number. Okay, so what do we have to do? We have to fix an EFT, something which is asymptotic to ADS, and then fix a cutoff, and then study all of the fields below the cutoff, compute one loop effective actions essentially, and then we should be done. That's easier said than done. There's a trick. If you're interested only in the log term, there's a trick that you can use so that you don't compute the full path integral of the light modes. You can use this heat kernel method, and essentially what you need to do is to compute this thing which I call A4 here, which is known as the width coefficient, and it can be expressed in terms of these 4 real numbers, A, C, B1, and B2 in our model. And so our job is to compute these numbers for all massive spins in ADS up to spin 2. What I'm glossing over here is that you could worry about zero modes and boundary terms because we're in ADS, but at the end of the day, all of these things are not important, so I'm glossing over them. I want to emphasize here that these C, B1, and B2 multiply something that is actually dependent. So this is the Weil tensor, the Ricci tensor, and so on. These are things that are going to depend on the details of the background of this asymptotically ADS4 background. But I told you that the log terms in the dual CFT have coefficients which are independent of the details of the background. And so just by using this very, very simple argument, you can argue that in a top-down holographic model, these numbers, C, B1, and B2, should vanish. And indeed, this seems to be true. So we went and we checked. So we took 11D supergravity on a sphere. So this will be dual to ABGM at k equals 1. And after some work, we computed all these numbers, and they indeed vanish. The thing that does not vanish is this AE number. It's actually a divergent number because we have infinitely many fields. So I don't really have a standard EFT because the internal sphere is of the same size as the ADS, and so I have to keep infinitely many KK modes, and for each of them I have a contribution to this A, and I have to add them up. And so it's, at the moment, quite confusing how to regulate this sum in a smart way, so I don't know how to do that, but if I choose it to be 1/3, I get an answer. I knew what's going to happen. Okay. I get an answer which agrees with all these other answers that I showed. So I postulate, thanks, that this is 1/3. We can talk about it afterwards. Good. So far, we've done some honest work, so I think we should relax and speculate. Well, I think honest work. So here we should relax and speculate a bit, and we did. So let's try to extract a lesson out of this. It looks like it's very hard in ADS to get something which is a coefficient of this log, which is independent of continuous parameters. So in QFT, such log terms, at least in 2 + 1D QFT, such log terms at large n should be some simple numbers which are independent of continuous variables. And if you impose this as a constraint on your putative holographic CFT with an ADS dual, you find some very strong constraints, which are, again, these C equal to B1 equal to B2 equal to 0. And it seems very hard to obey those things if you just randomly choose some ADS CFT. We checked this for many, many models in specific examples, and it works miraculously often. So I'm just wondering whether this can be promoted to some kind of a general Swarm-Landish kind of criteria. Okay, e to the minus square root of n or e to the minus square root of lambda effects, I don't have a lot of time. So what was done here is, well, not much. But in the QFT, we know that if you scale n with k and you have this lambda, the leading worldsheet instanton looks like this, with a very specific coefficient in front. And this can be done for S3 or for this TTI that I showed you. And you can wonder, what is this in the bulk? What it is a probe Euclidean string wrapping a P1 inside of CP3. The term in the exponent is its own shell action, and the coefficient has to be very carefully computed by quantizing the light modes of the string. And in the case with an S3 boundary, this was done in gory detail, and the answer agrees with this k square over 4 pi square. In the case of the black hole, we got something that looks reasonable, and we're still struggling with the numerical prefactor, but I hope we'll get there. The final thing I wanted to say is something that is non-BPS, or non-supersymmetric. The results above can be used to predict the corrections to the entropy of non-supersymmetric black holes, for instance, ADS Schwarzschild, embedded into this kind of M-theory top-down model. And here I chose to show you the formula for the ADS Schwarzschild entropy to this order at large n. You can also try to compute thermal observables in the dual ABGM theory. Here I'm showing you the 1-point function of the energy momentum tensor on this thermal S1 times R2 background. Good. That's essentially all I had to say. So what did we do? I showed you how SUSY localization can be used to exactly compute the path integral of ABGM on some Euclidean compact manifolds. I told you also how at large n, some of these results can be matched in the bulk. And this leads to some kind of interesting predictions, in some cases to all orders in G Newton, about the entropy of the Reissner-Nordstrom and Kerr-Newman black holes. Speculatively, we stumbled maybe on some interesting general constraint on EFTs in ADS. And then I told you that some of these things are kind of independent of supersymmetry and can be applied to learn something about non-SUSY observables. What I did not have time to tell you about is that none of this is very specific to ABGM. We have studied other models coming out of M2 brains with explicit bulk duals, and essentially everything I told you works fine. We can also do M5 brains. And there's a long list of open questions. I showed you some explicit analytic formulas, but many of them were not properly analytically derived, so it would be nice to do that. It would be nice to find some kind of an efficient way in the bulk to compute these SUSY observables. maybe there is a way to do socio-localization in the bulk. And maybe there is some type of OSV type conjecture for the entropy of anti-de Sitter black holes. We have a hint about this from many aspects of the story, but we don't know the full picture. Thank you very much.
Yeah, thanks a lot. Great talk, and thank you for bringing some art into the session. Yeah, 10 years ago there was also some art. Questions? Yes, please.
Hi, thanks for the talk.
Thanks.
Can you elaborate a bit on your comments on the scale-separated ADS vacuum? So is the message that you cannot satisfy these constraints on this bulk coefficients if you generate a gap, or what is the relation?
Well, I was kind of rushing a bit, so I didn't explain well. But essentially, if you have finitely many fields, their masses, so these coefficients C, B1, and B2, depend on the details of the mass spectrum of the light fields. So you're asking for some very finely tuned spectrum to achieve that. So if you don't have that, they will not vanish, which will imply that the dual CFT will have this exotic feature of having logs in the two-point function of whatever, local observables, which I don't know how to generate.
And finally, many fields, you don't mean the KK, you mean if you have other fields below.
You need, so this, I call it here log n, but it's really log, as I said above here, it's log L times a lambda, where lambda is your chosen cutoff. If you choose it to be the string scale, it will be a log lambda, so to say, corrections.
Actually, you may make a comment on scale-separated backgrounds. There is this higher spin ADS CFT, which, whether in some senses, ultimately scale-separated because there is only ADS4. And there, for example, so it corresponds to some ON model or UN model or gauged like QED3 type CFTs. And there it was possible to match the log n by studying the gauging of some.
That's an example where this thing works also, even though it's not.
The log n matches there. I think there is no n to the 1/2 in that case.
I don't think so,
Yeah, there is only like n and log n. Questions? Yeah, please.
Thanks for the nice talk. Some of these log corrections, high derivative corrections, can they be obtained from some externalization principle?
I'm not sure I'm understanding the question, but usually the extremization principles are associated with our ignorance about the exact superconformal R symmetry. So they don't teach you much about the corrections themselves. They're just a tool to fix the correct values of the things which I called delta 1, 2, 3, 4, and so on.
Thanks for the nice talk. I didn't quite understand. Do you have a first principles argument why C-log does not depend on all the charges, or is it just an observation on the theories that
If I had, I would have given one.
Okay.
It's an observation, so this is the speculative side of the talk. It would be nice if you find a counterexample, either log n or log of some marginal coupling appearing in the path integral with a coefficient which is a function of continuous variables. Right. But that's important. If the coefficient is a constant, it's fine.
And I guess it's not so easy to try to bootstrap that result because even the n to the 3/2 is sort of difficult. So
yeah, I would guess so. Yeah.
Thanks.
Yes, please.
Thanks for a nice talk. So this infinite sum you have, can you set a regularize? And if so, is the value 1/3?
If I could, and it was, I would have done it. If you do the most correct thing, the sum evaluates to 0. If you do the slightly incorrect thing of expanding this polynomial and then do the zeta function on each individual term, you'll get a non-zero value, which is not 1/3. But you're laughing too hard, okay? So I have... Sorry, I want to defend the sum. The honor of the sum has to be defended. It's one sum that I have to do, and I have multiple observables to match. So let's call this sum sigma, because it's a sum. And then let's assume that it's some value. So then I can do ratios of observables, and those will be scheme independent, and then I will not have to do a sum.
Yeah, actually, just had a comment about the bootstrap. I think it's very hard to bootstrap the sphere partition function, but now there is this new technique, fuzzy sphere, and that has been used to obtain results for some CFTs. So maybe that could be. Thank you.
You mentioned in the S3 partition function for the log terms, there's no black hole in the book but actually there is a topological black hole if you do conformal transformation to S1 times H2. There's a so-called hyperbolic black hole, which is due to L1.
Yeah. I was talking
about... So that
about...
may be related to log terms, maybe.
Yeah, that example will also have the same coefficient of the log. Yeah. But also it should be done when b is equal to 1 and delta is equal to 1/2. That specific example, I think.
Horacio.
The summing of the log terms of each mode, right? But generally, the log term of the thing that the high dimensions does not come from the sum of the logarithmic terms of each mode, right?
Right. So I should emphasize. I mean, I only had 25 minutes, so I cannot really tell you the full story. But in the special case of the round sphere, without any squashing or mass terms, this 1/4 log n. So this one was computed by Marcos and Ashok Sen and Alba and some other people, I think, properly. So they went to 11D supergravity, in which case, because 11 is odd, the logs arise in a completely different way. They come only from 0 modes, and then they carefully study the 0 modes, and that's how they got this 1/4. That analysis, doing that in the presence of all these deformations, is something that I don't know how to do. That's why we adopted this 4D Coates-Klein approach, which may or may not be rigorous.
But I think what you have to do is to regulate at the same time, the regulator and the sum both together, and then when both together, infinity, then you get it.
Yeah, I'll be happy to learn how to do it properly. So, okay.
Okay, this may be a good time to thank Nikolay again.